Welcome friends, Igor is here, and in this video we will take a first look at eigenvalues and eigenvectors. In this lesson we will define the eigenvalues and eigenvectors of a square matrix and consider some examples of eigenvalues and eigenvectors. Let's get started. If we have a square matrix A of size n and a column vector x of size n, then we can construct the matrix vector product matrix A multiplied by the vector x. The result of this product is another column vector of size n. We can think of this operation as a function. We have a fixed matrix A. As an input, this function takes a column vector x of size n, and as an output, the value of the function, it produces the column vector A times x. Let's look at some examples of this function, and we will adopt both algebraic and geometric interpretation in parallel. For example, we can take this standard unit vector 1, 0 and multiply this vector on the left by the matrix 1, 2, 2, 1. This results in a new column vector of size 2, and as you see, it has a different direction and different magnitude compared to the original vector. Let's take this second standard unit vector 0, 1 and again multiply this vector on the left by the same matrix. The result of this product is a new vector which again has a different direction and different magnitude compared to the original vector. So we can ask the natural question, is it always going to be this way? Will the vector change both magnitude and direction? Let's look at the vector 1, 1. When we multiply this vector by this matrix on the left, the new vector is the vector 3, 3. This is the vector in the same direction as the original vector. Algebraically, this means that the new vector is a scalar multiple of the original vector. The scaling factor here is equal to 3, and it tells you that the magnitude of the new vector is 3 times the magnitude of the original vector. Finally, let's look at the vector negative 2, 2. When we multiply this vector on the left by the given matrix, then the new vector has the same magnitude, but it changes the direction to the opposite. But it still lies on the same line as the original vector, and algebraically we can describe this as follows. The new vector is a scalar multiple of the original vector by the scalar negative 1. The scaling factor of negative 1 tells us that the magnitude remains the same, but the direction changes to the opposite. The last two examples are special in the sense that when we multiplied a vector by a matrix, the new vector was a scalar multiple of the original vector. And this is what eigenvalues and eigenvectors are about. Suppose A is a square matrix of size n, x is a non-zero vector of size n, and lambda is any scalar. Then the vector x is an eigenvector of the matrix A with eigenvalue lambda if the matrix vector product Ax is equal to the scalar multiple of the vector x by the scalar lambda. The reason we require the vector x to be a non-zero vector here is this. If you allow zero vectors, then any scalar is going to be an eigenvalue of any square matrix, because any matrix multiplied by the zero vector is equal to the zero vector, and zero vector is equal to its own scalar multiple by any scalar. Let's take a quick look at an example. We have this 2 by 2 matrix A and 3 sample vectors x, y, and z. When we multiply the vector x by the matrix A, we get the vector 2, 0, which is a scalar multiple of the original vector x by the scalar 2. This means the vector x is an eigenvector of the matrix A, and its eigenvalue is equal to 2. When we multiply vector y by the matrix A on the left, the resulting vector is the vector 0, negative 1. This vector is a scalar multiple of the original vector y by the scalar negative 1, and therefore the vector y is an eigenvector of the matrix A, and its eigenvalue is equal to negative 1. Finally, when we multiply vector z by the matrix A on the left, the resulting vector is the vector 2, negative 1, which is not a scalar multiple of the vector z. Therefore, the vector z is not an eigenvector of the matrix A. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will learn how to compute eigenvalues and eigenvectors of any square matrix. I will see you later.